All right. Somebody asked for a walkthrough, through the lab on Tuesday. So here we are going to do it. Question number one. The absolute value, usually denoted as bar x bar, the absolute value of x, can be computed using the following C function. The rest of this lab activity is to write assembly language code to accomplish the same computation. The first question is, then, how the processor can tell whether a signed integer is negative or not. So right here, this kind of ties into, um, oh, this ties into signed representation. So this, in other words, this is not by itself a really standalone lab because it does hook up to some previous concept that we have learned already. As an 8-bit number, which bit must be a 1 if a binary number represents a negative value? Bit 0 refers to the least significant bit if bit I is a 1 for all 8-bit pattern representing. Oh, if bit I is a 1 for all 8-bit pattern representing negative value, what is I? Alright, so so it's asking for the bit position. And I was going through some of the attempts from certain individuals of the class, and I'm going to have to say I'm a little worried because some people just kind of gave you some random guesses like negative numbers. Now there are negative positions, but those are basically the fraction part of a value, and in this case, because we're dealing with an integer, so they really should not go negative. So the correct answer is the most significant bit, which is also called, guess what? The sign bit. So that's bit 7 in this case. Because there are 8 bits, we count from 0, which is stated right here. Bit 0 refers to the least significant bit. So I is supposed to be 7 because that is the sign bit, the most significant bit. Alright, moving on to the next question. Our second task is to check the sign bit of a number. There are many ways to do this, but I want the least expensive method in terms of the number of instructions. This generally means avoiding the use of instructions that has immediate operands. So that would be the LDI instruction, to use an immediate operand. To get to the instruction we need to use, we first need to examine the ALU itself, which flag the corresponding ALU tunnel name is in parentheses. In the ALU reflects the sign bit if the result of a computation of the result of a computation regardless of the computation with the exception of the instruction decrement and increment. Alright, so you can go through the whole thing. You can actually go through Logisim. Let me see if I still have Logisim up and running. I do. Alright, so here's Logisim up and running. And we want to look at the sign bit. So I'm guessing some people actually try to guess this one too instead of actually working it out. I'm gonna have to say, that method may not work out very well for the exam because the lab is really trying to guide you through the process of understanding the architecture. So anyway, this is S out, which is the sign bit, and it's basically looking at bit 7 of the result of the computation. Alright, so let's get back to the question. So the question is, the correct answer is S out. Okay, the sign bit is basically S out, corresponding to the tunnel called S out. Moving on to question number 3. Let us shift our attention to some other instructions. Certain combinations of operands do not do much with certain instructions, such as AND AA does not do anything useful. The same applies to OR AA. This is why the opcode of some combination of operands is in quotes hijacked to do something else. So the term hijack, is also further explained in the next paragraph, but I explicitly, explained what hijack means, in this context. Note that the assembler is rather dumb and cannot understand opcode hijacking. This means it is possible that two instruction mnemonics can assemble to the same binary opcode. This weakness of the assembler can help you confirm your answer. So TAC remembers that the opcode of either the AND XX or the OR XX family are hijacked for other instructions. Analyze the opcode table and find out which family is hijacked. Alright, so there are a few ways to answer this question. So the so the answer is either AND or OR. Unless I really try to be tricky and turns out to be both or neither. So one way to find out is to look into the opcode table, and we can start with AND. Okay, so we'll look for the AND instruction here. So the AND instruction family starts with 1100 and then 4 bits representing which is register X and which is register Y. And so if X and Y are the same registers, then we end up with 0000 for XXYY, 0101, 1010, or 1111. So what we are really looking for is to see if there are other instructions starting with the bit pattern of 1100. Alright, so the quickest way to do it is to use a search, which is Control F, and then you type in 1100. And as it turns out, this is the only family of opcode that starts with 1100. So that's pointing in the direction of and XX is not hijacked because no other opcode is using the first. They're not having the same for first. The most significant 4 bits are not the same as the AND XX type of instructions. But just to confirm, we want to look at the OR instruction as well, just to make sure that that one is indeed hijacked. So we look for OR, and we need to look for OR. There we go. So this is not, and then we have. Okay, where's the OR? That's not. Right there. So this is the OR instruction. So the OR family, OR instruction family starts with 1101, and we can see, there's another family, which is also starting with 1101. So that's how we can confirm that OR XY is indeed hijacked, because OR AA is actually increment A, because OR AA would have been 11010000, but increment A would also be 11010000. So this is the one that is hijacked because OR AA doesn't really do much. And so the answer to this question is OR XX. So this is the correct answer here. And then moving on. Question number 4. Combining the result of the previous 2 steps, now we have an efficient way to check the sign bit of a register is set or cleared. Let's call the mnemonic of the instruction that is not hijacked test XX, and it updates the S flag according to the bit pattern of register X. Because basically what it does is it pushes register X through the ALU, and anything that goes through the ALU will set the S flag accordingly, other than increment and decrement. So that means we in the flags register, the sign bit, the S bit, is going to reflect bit 7, which is also the sign bit of whatever register we are pushing through the ALU. Note that the mnemonic test does not exist. It is just a placeholder here so that the question of one step does not answer another question. Because if I had mentioned this as AND, then I would have answered the previous question already. This means the following sequence of mnemonics can be used to make a decision based on whether a register has a negative value when interpreted signed. So we have a no op instruction here, which is necessary for the CLI trace to work. We have K1 defined to be 4, which allows us to easily change what value we are testing. LDIA K1, this is basically the initialization of register A to the value of K1, which in this specific case is 4. And then test AA is going to push the value of the register through the ALU. So in this case, the sign flag is not the only flag that is going to be affected. The Z flag is also going to be affected because the Z flag is also affected by anything that is going through the ALU. At this point, you may want to write some code, assemble it, and test it in the simulator to make sure that this sequence of mnemonics does work as expected. Use register A specifically and initialize it with an LDI instruction and the label K1, so which is all this is doing already. Now we are ready for the next step of this program. How do we perform arithmetic negation? Specifically, what is the name of the following value with respect to the bit pattern X? Now this is also getting back to the signed representation module. So this is actually called 2's complement. There we go. And I think I see some people, actually sequentially testing the options and see which one is the correct answer. That may be an effective way, to answer the questions, in a lab, but it's not going to be very helpful, when it comes to the exam. So I think it is quite important that we associate concepts from this lab with the topics and the concepts that we have learned so far from the other modules. All right, click on next. So this is the last step. Now you need to look into the instruction set of the TTP of text toy processor and figure out how to perform bitwise NOT +1, and X is a register, and integrate that with the code from question number 4 to check the sign of a number, perform the operation in place, meaning that register X stores its own absolute value after the code. The program should stop at a halt instruction. Your code may contain multiple halt instructions at this point. The register that contains the value to find the absolute value is register A. Upload your program, in terms of the source, not the opcodes. The absolute value should also be stored in register A. So we start with the initialization of register A to K1, and then when the program halts, we want the absolute value to be in register A as well. For this question, submit a text file that has the mnemonic of instructions, the content that you paste into the source sheet. Make sure this code meets the following requirements. Start with a no op, use register A as the register providing the value. Write the code to check the sign of register A. If it is 0, the program can halt. Otherwise, use instructions to arithmetically invert the sign of the signed value of register A, then halt. To test the program, use label K1 to define the test value. My testing script will change the definition of this label to see if your code works for various test cases. Right after the first no-op instruction, use LDIA K1 to initialize the value of register A. Make sure your program halts after getting the absolute value computed. You can use any number of halt instructions in this program. Alright, so let's go ahead and try to get this done. So let me find a command line interface that is suitable, like this one here. Alright, so I'm going to start a new tab, and we'll call this program just ABS. There we go. And I'm going to use the extension TTP ASM, which signifies this is an assembly language source file. So so the editor would use the correct syntax highlighting in this case. So we start with a no-op instruction, which is necessary for tracing, and then we define K1. And we can define K1 as -5. So basically, we use a symbolic name to define the value that is being tested. So we have LDIA with K1. The first thing we do is we use AND AA. Basically it is the quote-unquote test instruction. So this is going to push register A through the ALU, and therefore affecting the Z flag as well as the S flag. Now the Z flag is not useful in this case. Only the Z only the S flag, the sign flag, is used. So then we use JSI to a particular label. Now, your label name doesn't have to coincide with mine, so I'm just going to use a meaningful label name here. So this is going to go to negative, and which means if it did not go to negative because of the JSI instruction, it is non-negative. So I'm using a line of comment here to remind myself, what does it mean if I did not perform the branch to negative? Now, obviously, it is also necessary to define the label negative and then put some code here. And I'm going to start with a comment here to basically say the value is negative here. And this one is the value is non-negative. So if the value is non-negative, the value is its own absolute value already, and I can just halt here. On the other hand, if the value is negative, then we need to arithmetically negate it. There are two ways to do this. The easiest way is to utilize a bitwise NOT, which is 1's complement. So we have a NOT A, and then we add 1 to A, which is increment A. That's the easiest way to do it, is to perform a bitwise NOT followed by an increment, and we're done. So here's halt. All right, so I have just written a program that I claim that it's going to find the absolute value and then put it back into register A. The question is, does this work or not? So we're going to test it using River Spider. So we'll go to, I'm going to set up a path correctly or put an alias into my bin folder at some point. Well, let's do it now, okay? Because might as well get it done now. I have a little bit of time before my next class starts. So I'm gonna go to my bin folder here, and we'll just do a symbolic link to my documents CISP310 River Spider submit.sh, and then we'll just alias it as submit.sh. There we go. Alright, so now we can get back to the temp folder. Oh, I just made a mistake. Alright, so let's go back to the temp folder, and now we can do a submit.sh and then the name of the file, which I think is abs.ttpsm. So I run this through, and this is using the assembler that is published. So that means it is actually using the assembler that all of you can see. So let me go back to the tab, and it's working, and we can see how register A ends up with the absolute value of 5. So now the question is, does it work when A is initialized with something that is not negative? So we'll give it a try. So let's say it is initialized with say 15, right? 15 is non-negative, and we're gonna run the program again. So you can kind of see how this really helped to streamline the entire process, because I just have to say, okay, here's the source file, go ahead and assemble it, run it, and then give me the trace of it. So now I can get back to the trace, and in this case, A is 0F, which is the hexadecimal representation of 15, and it stays that way too, when the program halts. So the program does work in this case. Alrighty. So I'm going to upload this, and if you guys, if you are having issues, like having difficulty understanding the concepts right now, it's probably a very good idea to go to the Beacon tutoring sessions. Particularly, it's important to connect what we are learning now with all the previous modules. Basically, everything from before, it's still relevant. I'm not going to specifically test you for things that we have introduced in the past, but it doesn't mean that it's not going to be a part of something that we're going to do now. So it is essential that we maintain the knowledge of what we have learned so far. Alrighty, I'm going to upload this video so that you guys can take a look at it.